Today we're going to be going over the ACSL topic of assembly. Assembly is a programming language. It's been adopted in ACSL to a more simplified format, but it's generally applicable, the concepts at least. In the real world, the assembly language that you'll see is a little bit more intense, and so the one in ACSL is not so hard to tackle. In assembly, there's a specific structure when we execute a line of code. We're going to have three components: the label, the opcode, and the lock. Out of those three, the opcode will always be present, and the label and lock can be absent under specific circumstances. The label is an alphanumeric string that begins with an alphabetic character. It's used as either as the name of a variable or as a reference for a line of code, and you'll see how that manifests itself later. The opcode is equivalent to a function in other programming languages. It tells us what to do with the data that we have in the label, the lock, and the accumulator, which I'll get to in a second. The lock is the argument for the opcode, so it'll contain a string, a number, any data that will be operated on by the opcode, except for in one case, which I'll also show you later. The accumulator is a special location in the execution environment of our assembly program. We do have opportunities to store data in specific variable names, but the accumulator is basically a variable that is omnipresent in any assembly problem that you're going to see. So let's go over the first set of opcodes, and I'll explain them as we go through. Load is our first one, and this is the first in the set that have to do with variables and storage. So load will take the contents of the lock and place it in the accumulator, and the lock is also unchanged. Pretty straightforward. Store does the inverse. It takes the contents of the accumulator and places it in the variable as referenced in the lock. The accumulator remains unchanged. DC, the value of the memory word defined by label, is defined to contain the specific constant in the lock. The label field is mandatory for this opcode, so DC is essentially just, as you would see in other programming languages, a variable assignment. A is equal to B. In this, it would be A, D, C, B. Read. This reads a signed integer into the lock the same way that you would take an input in another programming language from the terminal. And print is an output. In the context of ACSL, you'll see print used as like the question asking you what's the last thing the program has printed. And here are a few of the arithmetic functions. These are pretty basic. The thing to note though is that they modify the lock, they modify the accumulator and not the lock. So if we're to perform add, and suppose we had add 8, and right now our accumulator is 2. After we execute this line of code, our accumulator is going to equal 10. Sub works the same way. The contents of the lock are subtracted from the contents of the accumulator, and the difference is stored in the accumulator. You see at the end of these, addition is modulo 1,000,000, subtraction is modulo 1,000,000. That's basically just like the range of values that can be within there. The contents of, for mult, it's the same thing for multiplication. The contents of block are multiplied by the contents of the accumulator, and the product is stored in the accumulator. And div is equivalent as well. So here are a few of the meta functions, and I just categorize them as such because they're to do with the execution of the program. And these are the most interesting functions, I think, or opcodes, I think, in assembly language. These are functions that you would use in the formulation of a loop or something like that. So the first of these is BG, and this branches to a function, to an instruction labeled with lock if the accumulator is greater than 0. And the way I remember these is BG, or like be greater. This one is if the accumulator is equal to 0, we branch to the instruction, so be equal. And this one is branch to the instruction if the if the accumulator is less than 0, and so be like less. And then this one is simply branching to an instruction irrespective of the value of the lock. And then finally, end is just the program terminating. This one's special because the lock field is ignored, which is the case that I mentioned earlier. So let's move on to some examples. This is an example from the ACSL webpage. So first thing we're going to do is I see that we have 4 variables here, and the way that I like going out about problems like this is constructing a table of sorts with each of these variables. So we'll say temp A, B, C. We see in these first 4 lines of code, we'll have this be 0, 8, -2, 3. This might seem trivial for a problem like this, but it's important to note that these problems will increase in scope a lot often, and so we want to stay organized at all levels of problem solving. We'll also put a column here for the accumulator. The first thing we're going to do is load B into the accumulator. Then we're going to multiply it by C. Oops. So I'll do that on another line of this table, and then the accumulator will become -6. I'm just going to leave this line blank because none of the other variables are changed. We're adding A, so that becomes 2. Then we're dividing by B, this becomes a -1. And then we're subtracting A, becomes -9. And finally, we're storing that into the temp. And so the temp also becomes a -9. After the following program is executed, what value is located in temp? And that is -9. Nice. This is a problem for a previous ACSL contest. We're going to start by constructing our table again. And here we have S, N, and the accumulator. We start on our first 2 lines of execution by saying that S is 0, N is 10, and our accumulator is 10. Now we're going to multiply the accumulator by N, and our accumulator becomes 100. Now N becomes, now we're adding S to the accumulator. It's just going to remain the same. I'm not going to add another line. And now we're storing the accumulator in S. We're now going to load N again. So 100, 10, 10. And we're going to subtract 1. Now we're going to store that back in N. And our accumulator is greater than 0, so we're going to branch back to this line. Okay. We already have the same value in N, and we're multiplying it together. We're adding 100 to the accumulator. We're storing that in S. We're loading N, we're subtracting. This will become 8. And then we're storing that back in N. Okay, so now you might see that we're developing somewhat of a pattern here. And because we know this is going to repeat until N is equal to 0, we can go ahead and skip having to do all of these steps and just see that it's going to be 100 squared plus 9 squared plus 8 squared plus 7 squared plus 6 squared plus 5 squared plus 4 squared plus 3 squared plus 2 squared plus 1 squared. Okay, and I'll go ahead and do this out. We're going to be getting 100 plus 81 plus 64 plus 49 plus 36 plus 25 plus 16 plus 9 plus 4 plus 1. And I'll go ahead and punch that into my calculator. And that gives a final value of 385. What's important to take away from this problem is that if we can simplify and see just what the results of our assembly program is going to do, then we might as well just skip these steps. These assembly language questions often take the most time on the test, and if you can allocate some more time to spend reviewing other problems, it would be advantageous to you. As always, remember to review the sheets, to look over the ACSL wiki page, which is extremely helpful, and good luck.